Good morning, students. This is Anil Kumar Panta. Today, we'll discuss shape functions and compatibility of shape functions. In order to discuss shape functions, we have to see coordinate systems. So, coordinate systems. We have global coordinate systems and local coordinate systems to define an element. To define an element with space, location of an element will be referring some axis. There must be some origin point. To refer an element, there must be a thorough reference. We call that as coordinate system. When we go for a global coordinate system, in the representation 1, it is seen outside, whereas in the representation 2, it is on the element. So, global coordinate system is of the element, local coordinate system is on the element. Now, let us take two elements for global coordinate system, a rectangular element and a triangular element with points x1, y1, x2, y2, where the next it is x1, y1, x2, y2 and x3, y3. Now, not exactly on the element, if the axis is located at a distance, we suggest or say it is a global coordinate system. But if the axis is located on, that is, at the extreme end point towards the left, if the axis is located, then it is a local coordinate system. Now, if the element is a rectangular element, if the length of the element is L, then one boundary is 0, the other boundary length is L, total length. So, the extreme end is L, the initial boundary is 0. Now, for a local coordinate system, the axis can be varied inside at any region. Similarly, for a global coordinate system, the axis can be varied at any distance outside based on the necessity. In some cases, I am drawing an L section. First I have represented L vertical rectangle, then I have to go for horizontal rectangle. So, we are going for global coordinate system. So, some axis is represented outside. So, vertical rectangle I have represented. Then I go for local, taking the axis to one extreme end. From there I will be going for horizontal rectangle. Now I am using both global and local to represent an L section, an L element, an L section. For the second thing, when I go for midpoint, local coordinate at midpoint, that is, the axis is represented such that I call that as 0, origin, starting point. So the left side I am taking as negative, right side I am taking as positive. This left side part I am calling as minus L by 2 half. For a full I am taking center, so left side is half, right side is half. We clearly understand that the boundary conditions for this are minus L by 2 and plus L by 2, not 0 to L. Why? Because of the location of local coordinate system or axis on exact center. Next, let us go for natural coordinate system. In a natural coordinate system, it is also a form of local coordinate system that permits the specification of a point within the element by a set of dimensionless numbers whose magnitude must never exceed unity. So I go for 0 or 1 in FEM. I'll be going for 0 or no and 1, but not the other elements which are located in between 0 to 1. If the magnitude is exactly unity, then I suggest it as natural coordinate system. Previously I have taken as x distances in terms of length. Now I am going for magnitude, so I take a symbol zeta, which is a representation of E, pull it down, so it is a Greek symbol which is zeta. Now if the axis is located on the element towards one end, so zeta is 0 and 1. If zeta, natural coordinate system, zeta is exactly on center, the extreme boundary conditions are -1 and +1. This is also a local coordinate system, but magnitude we are taking as 1. So it is zeta. So every part will be taking as +1, -1, +1 and -1. Next, shape functions. Shape functions are employed to find out the displacements at interior points of element using the values of nodal displacement. I take an example that we are going for a sine curve. I brought up the example that I kept a stone in water. Definitely ripples of water will come, means on a line there will be displacement up as a ripple curve and also down. When the progression of it is continuous, I say that is a sine curve or a cosine curve. Means every particle on the line is displaced for a positive ripple up, for a negative ripple down. Means we are getting some shape, parabolic shape. I am taking that as shape. The mathematical equation which is pertaining to this shape is a shape function. Now, every displaced node is u1, u2, u3 local displacements with shape functions are represented as global displacement u, as u is equals to n1 u1 plus n2 u2, so on and so forth. Now considering a bar as 1D element. Now when it is a 1D element, clearly we see that the element is having node 1, node 2 and the center let us bit as one more node, node 3. With reference to global coordinate systems, the nodes were located in distances x1, x2 as shown in the figure. Similarly for natural coordinate system, zeta is equals to -1, 0 and 1 for nodes 1, 2 and 3 as clearly shown in the sketch. Now I am going for interpolation functions. You can go for linear, parabolic or cubic interpolation functions such that we'll be joining this nodal displacement showing a shape. Now for the first case, I take u as unknown because we are getting a curvature in between u1 and u2. Whereas for the second, we are going for zeta values as -1 and 1. So I am getting exactly linear, u1 and u2, u as linear. So let us insert some equation. So when I insert an equation, I will be going for a linear polynomial equation such that it is u is equals to a1 plus a2x. Linear polynomial equation. If we go for cubic, it will be x cube. Similarly, other equations. For absolute system or global system, u is equals to a1 plus a2x in terms of x, y or z. For natural or intrinsic, it is u is equals to a1 plus a2 into zeta. Now let us go for absolute coordinate system to check the shape functions. When we go for absolute coordinate systems, let us go for cases, boundary conditions. We are getting two boundary conditions at node 1 and node 2. Center node is node 3 where it is 0. So x is equals to x1, u1 or the boundary conditions, means the distances. The distance of first node from the axis is x is equals to x1. The displacement at that point is u1. Similarly at node 2, x is equals to x2, x is equals to x2 and displacement of the node 2 is u is equals to u2. That's what we have taken here. Now putting these boundary conditions in equation A, so the equation A transforms as u1 is equals to a1 plus a2 into x1. I kept u1 comma x1 at node 2, u2 comma x2. Mathematical solving, subtracting 1 minus other 2, will be getting a2. Now putting a2 in either equation 1 or 2, will be getting a1. Now after getting a1 and a2, submitting in equation A, then you will be getting u. Slowly on expansion with LCM splitting, we will be getting u as u1 into x2 minus x by x2 minus x1 plus u2 into x minus x1 by x2 minus x1. We know that equation is u is equals to n1 u1 plus n2 u2, where n1 is equals to x2 minus x by x2 minus x1 and n2 is equals to x minus x1 by x2 minus x1. Dear students and viewers, we must remember and memorize n1 and n2. Next, let us go for natural coordinate system. U is equals to a1 plus a2 into zeta. At node 1, it is u is equals to u1, zeta is equals to -1. Let us go there. At node 1, u is equals to u1, zeta is equals to -1. At node 2, u is equals to u2, zeta is equals to +1. Boundary conditions, extreme end conditions. When we take boundary conditions, we will be getting the shape of the curve. Now, putting the boundary condition in the equation, two boundary conditions, u1 comma -1. So the equation transforms to u1 plus a1 plus a2 into -1. So it is u1 is equals to a1 minus a2. Similarly, at node 2, we got second equation. Solving the above equations by addition, because one it is having plus, other is having minus, automatically one term will be eliminated. So the leftover is u1 plus u2 is equals to 2a1. From that I am getting a1. From the basic mathematics we know that we will be getting a2 on submission in equation 3 or 4. So we got a2. To get the net representation, we will be putting a1 and a2 in B. So after getting this, splitting of the equation, so that net equation is u is equals to u1 into 1 minus zeta by 2 plus u2 into 1 plus zeta by 2, where n1 is equals to 1 minus zeta by 2, n2 is equals to 1 plus zeta by 2. These things we have to remember. Students and viewers have to remember n1 and n2 as 1 minus zeta by 2, n2 is 1 plus zeta by 2. Next, let us find out for zeta. Initially, we have checked for displacement u. So, u equation is a1 plus a2x as linear equation, linear polynomial equation. Now, whatever you want. Instead of u, you want f of x is equals to. If you want y, y is equals to. If you want zeta, it is zeta is equals to. Zeta is equals to a1 plus a2x. So, you want to find zeta value. Now, the boundary conditions of this element, the element is 1, 2, values of zeta or minus 1 plus 1. Similarly, we will be representing boundary conditions as node 1 minus 1 x1, node 2 plus 1 x2, submitting in above equation. Zeta is minus 1 is equals to a1 plus a2 into x is x1, so x1. Similarly, 1 is equals to a1 plus a2 x2. Mathematical analysis, solving the two equations. So, subtracting of two equations, if you add, it will be an equation in A's and A2's, so it is of no use. Subtract, one constant will be terminated, so we will be getting A2 as A2 is equals to 2 by x2 minus x1. Submitting in as the two equations, we will be getting a1, submitting a1 and a2 in zeta is equals to a1 plus a2x, we will be getting zeta. Zeta is equals to 2 into x minus x1 by x2 minus x1 minus 1. Now let us check the compatibility. Kronecker delta property. When we check the compatibility, when x is equals to x1, x is equals to x2, n1 is equals to x2 minus x1 by x2 minus x1. Where it have come from? So this is the part. n1 is equals to x2 minus xy, x2 minus x1, and 2 is equals to x1, x minus x1 by x2 minus x1. From this, we are going for compatibility. At node 1, we will be having the magnitude at 1 as 1, so other part is 0. What is the meaning of 1 and 0? See, it is clearly displacement of node 1 is 1, other part is 0. We went for mathematics as linear polynomial, so we joined it. So it is representing as a right angle triangle. Similarly, for N2, we are getting a right angle triangle with node 2 displaced to 1. Node 1 is 0, node 2 is 1. Similarly, for putting zeta value, n1 is 1 minus zeta by 2, n2 is 1 plus zeta by 2. Node 1 is displaced to 1, node 2 is displaced to 1 here. Now, in order to check the completeness, n1 plus n2 is equals to 1. So, submitting the value of n1 plus value of n2, Definitely we are saying that is equals to 1. Similarly, n1 u1 plus n2 u2 is equals to u. That is n1 x1 plus n2 x2 is equals to x. So on submission of n1 and n2 we are getting x. Now let us check the compatibility. Mixture of these shape functions. For the stiffness of element, we have to go for mixture of or repetition of the same shape function. Triangle plus triangle plus triangle plus triangle. That is what called in ANSYS meshing. So now the linear function is represented with two parts, u1, 1 and 2. So the boundary conditions are at node 1, x is equals to x1. Similarly, u is equals to u1. At last boundary, extreme boundary, x is equals to x3, u is equals to u3. Similarly, at the center. So I split this into 2 and I am checking as u is equals to n1 u1 plus n2 u2 for the first split. For the second, I am going for u is equals to n2 u2 plus n2 u3. So submitting n1, n2 for u dash, n2, n3 for u2. So when I put x is equals to x2, the meaning of it, we are joining the two. Now to obtain the linear equation, we have to join the two. The second subset of linear polynomial, and the first subset for the second linear polynomial curve, when we join it, at the middle it is equal, x is equals to x2. So submitting x is equals to x2, for u dash we are getting it as u2. For u2, u to the power of 2, we are getting this as u2. So this compatibility we have checked. As n1 x1 plus n2 x2 is equals to x, n1 plus n2 is equals to 1. In this lecture, we have discussed coordinates and shape functions by checking the compatibility. In the following lectures, we will be seeing the problems on this coordinates and shape functions. Thank you all. Have a good day.